Okay, hi everyone. Welcome to the last lecture. You've made it through the semester. We have made it through the semester. Um, so what we're covering today is we're looking at generative adversarial networks. One of the reasons why I covered this topic at the very end of the semester is this is such an active area of research that I'm almost guaranteed that anything I say at any level of specificity about this topic will almost certainly be shown to be otherwise very soon after after this class. There are new techniques being developed. There are new results being presented. So it's an exciting area. Hopefully, some of the things that I'll show you are still applicable even when new methods come out. This is not a particularly dense or math heavy class. Hopefully this will be lightweight, and then we'll look at just a look back. Okay, so let's take a look at generative adversarial networks and GANs, and let's take a look back to see how they fit in. Remember that we have looked in the semester at supervised learning, which is the idea of learning, X to Y mappings with an explicit supervision for what Y should be, and when you make a mistake, how much that mistake costs you. So Y hat versus Y, full supervision of that. Reinforcement learning, which is learning to act under evaluative feedback. You can force, there are lots of function approximation problems in here, but really you only get reward ST, AT, and maybe ST plus 1, depending on how it's formulated. But you only get rewards for the actions in the states that you visit. You simply do not have supervision on alternative states that you could have gone to. So it's a lighter amount of supervision. There is a notion of acting and decision making. Unsupervised learning is about discovering structure in the data. The training data does not include any sort of desired outputs at all. And we've been looking at density estimation as our primary object, and generative models in particular. And we already sort of introduced this taxonomy that there are implicit density models and explicit density models. We've looked at pixel RNN, CNNs. We've looked at variational autoencoders in a couple of lectures. And today we'll be crossing over this boundary on the other side to look at a family of implicit density models called GANs, or generative adversarial networks. The sort of main story so far, and the main sort of pitch is going to be explicit density models like pixel CNNs or pixel RNNs define an explicit likelihood function. They construct P sub theta of X, your random variable or your object, image, text, anything that you're trying to model. They construct a likelihood function or a probabilistic model over just that piece of data. VAEs, the second class of models we looked at, construct a joint model over the variable in your data set and the unobserved or latent variables that are introduced by us, the model designer, as certain quantities that, although we do not observe, surely must be playing a role. We then ran into a bunch of problems about not being able to optimize this correctly, because the likelihood function then requires marginalization, which can be integration or summation, depending on discrete or continuous Z. And then this led us to deriving a lower bound on the likelihood and all sorts of other problems. Okay, but at this point, you can take the stand and ask the question, look, all this difficulty seems to be arriving because we are trying to get a handle on a likelihood function, P theta of X. How about we give up on that? How about I don't ask for a P theta of X? How about all I say is, can you procedurally sample? So maybe all that I want is to be able to produce samples from my model of my data. So maybe I'll call this X or X tilde. This is, in an autoencoder notation, the output of the autoencoder. Can you just produce samples? And all I want is that these samples should look like what I would have gotten So not the model. This is the data. So the true data generating distribution, I don't have a handle on that either, right? The world is what the world is. I don't have a probabilistic model describing the world, but I know I can sample really easily from it. I attach some sensors on a robot and I get some data. I download some images from the web. I ask people to write some sentences, and that for me is a sampling function. So if I can sample from the data generating distribution, what if I was okay with you giving me a black box? So you do not give me a p theta, you give me a black box. So x tilde is coming from a black box function that I don't know what happens inside it. It doesn't have a probabilistic interpretation, but you'll be able to sample from this black box. Now, as you know, we know very well, as soon as we hear black box, it's pretty clear what's going to happen, right? That black box is going to be a neural network. It is going to have some parameters theta. It is going to produce output x tilde. So that part is clear because we want to sample. What part is less clear is what that black box will take as input. And when it produces a sample, how we will compute loss of x tilde, right? Are we going to, for example, remember we are given a data set of data points, right? Are we going to compute, in autoencoders, we compute L2 loss or reconstruction error. What is reconstruction when we are not trying to reconstruct anything? What do we measure loss with respect to? We have no ground truth. What sample were we trying to produce? If we don't have a correspondence or an alignment, this sort of loss is difficult to define. How do we know what we were trying to construct? And how do we know this is a good sample versus a bad sample? We can't compute log likelihood. We can't compute KL divergences. We can't compute L2 or any other metrics that require any sort of correspondence. So loss is a problem and input is a problem. And those are exactly the two things that we will show you how to solve. And those are the two ingredients that go into generative adversarial networks. One thing I again want to highlight is GANs do not work with an explicit density function, which means that you cannot ask questions like, what is p theta of x? This seems, trivial, that, yeah, I understand that we can't ask questions like p theta of x. But this causes problems. It means that there is no way to measure the likelihood of a data set under your model. Your model just cannot answer those questions. Your model cannot do auto-completion either. There is none of these queries either, because there is no p theta of x, so there is no p theta of xi given xj. There's no auto-completion, there's no notion of certainty, there's no, on a held out set, what likelihood does your model assign? None of that. And so this is we have to be aware that we are making this trade-off, that we do not have access to these quantities. Okay. All right, so GANs then consists of the following two ideas. And just like with VAEs, what I've done is I've sort of disentangled those two ideas and we will see them separately. One of them is about defining a loss function, and one of them is about what is the input to this neural network that is going to produce a sample. And those are the two ideas that are independently useful, meaning that you will find in some papers that they use adversarial training but not learning to sample, and in some other papers they will use learning to sample but not adversarial training. And in majority of papers, the original GAN paper and the follow-up, both ideas are used, but you should be aware that these are two completely detached ideas, that you could use one and not the other. Okay. So let's take a look at the first one, the learning to sample idea. How do we feed into a neural network some input that gives us some output that is a sample from a random variable? And in order to build up to this idea, we'll play a game. So this is what I call the easy interview question. So let's say, imagine yourself, you're done with this class. You have taken the deep learning class. Now you're all set. You're going to apply to either a ML position in some company. There's a coding interview, and they sort of bring you in and they tell you, here's a coding question or a programming question. I give you a sampler from a uniform random variable, meaning a random variable between 0 and 1 with uniform density function. And what you have to do is use this uniform random variable sampler to produce a sampler from a Bernoulli distribution with a particular parameter. Just a reminder, a uniform distribution is continuous uniform between 0 and 1, has a density function of 1, and you can say the probability of u lying in any set a comma b is the b minus a, the length of that set for a less than equal to b equal to 0. So that's what we mean by a uniform distribution on this interval 0 to 1, that any length of that subinterval is equally likely, is proportional to the length of that subinterval. So you get a uniform random number generator. I give you a sample from it, and you have to define a function that is uniform to Bernoulli. And remember, Bernoulli is this function, the random variable, where probability of x equals 1 is equal to theta, and probability of x equals 0 is 1 minus theta. So this is the input. You get a u. You have to write this function that outputs an x. So in the chat, if you have ideas on how you might solve this problem, feel free to write it out as a program, in sentences, in a couple of words. This is a simple sort of a thing. We'll get to the harder interview question next. So I'll wait a few seconds. And so the trick is to realize that you can basically convert the 0 to 1 interval into two intervals. You can have one interval of length theta and another interval of length 1 minus theta, and what you can essentially do is ask which subinterval did you fall into, and because the length of those intervals are proportional to those states, that you can just assign them. So you can say if u is less than equal to 1 minus sorry, not less than. If u is greater than 1 minus theta, return 1, else return 0. And by the way, this is just a rephrasing of the answer in the chat. I've written this with a greater than symbol and a greater than 1 minus equal to, as opposed to a less than theta. This is just to I'm sort of thinking ahead another slide, and I'm going to generalize this, so I'm sort of setting it up this way. But it's just to find out, did my u fall into this interval or did my u fall into this interval? So I'm just checking for this point, which is the 1 minus theta point. And so if it's greater than 1 minus theta, then it falls in the theta length interval, and therefore I return 1. So the probability of achieving 1 is exactly equal to the length of this interval, which is exactly what we wanted. And the probability of achieving 0 is equal to the length of this interval, which is exactly what we wanted. So that part's easy. This is a simple question. Here's a slightly harder variant of that question, which is that I give you that same uniform number generator, and what I ask you now is to produce a sample from a categorical variable with some parameter pi. And remember that a categorical variable has this parameter pi1 through pi k. It's a k-way categorical variable. So each pi sub I is greater than or equal to 0, and the sum of pi I equals 1 through k is 1. So it's pi is a point on the simplex, and now the question to you is, how would you generalize the previous approach to use a uniform sampler to now sample from this categorical? And you can again write pseudocode if you want, or describe it in words in the chat. The intuition is exactly as said. It's a generalization of the previous idea. You take the 0 to 1 interval and you break it up into k bins or subintervals, and they will have length equals pi1, pi2 till pi k, and which means that, so these are the subintervals. When you get a u, all you have to check is what subinterval you have fallen into. Notice that as far as these subintervals are concerned, their endpoints are pi1, pi1 plus pi2, and sort of the cumulative sum. And so checking for subinterval is essentially return j such that you're given a u, return j such that the sum of pi I equals 1 through j minus 1 is less than equal to u, which is less than sum of pi I equals 1 through j. So these are essentially cumulative sums. Those are the interval endpoints, and we are essentially checking does u, what is the j corresponding such that u is greater than the left interval endpoint and less than the right interval endpoint. And notice that I'm doing a careful treatment of the less than equal to and the greater than equal to and less than, because it matters what the endpoint is. At 0, you still get, you want that to be included in the first bin. So this is just checking for which interval you're in. So this is the sort of program you write. Now the question to ask, which I think a subset of people are already getting to, is does this remind people of something? What does this object, what is this object? Summation of pi I going 1 through j. We know this in terms of random variables. This is a property of random variables, or a function that can be computed on random variables. This is the CDF of x, of our random variable, of our desired random variable x. It's giving us the probability of x less than equal to some t, and this is what that t is. And this entire operation is essentially computing f inverse of u, because f, the CDF of our desired random variable x, is a step function. It's a function where if I write 1, 2, 3 all the way till k, there's pi1 here, pi1 plus pi2 here, and so on. This is the CDF f of x, and this entire operation is essentially just computing f inverse of at a particular value u. And this thing we've been building up towards turns out that this is not a fluke. This is the InverseCDF sampling theorem. It's sort of one of the first few things that people are taught in a class actually introducing random variables and sort of continuous distributions and stuff, but people forget, and it's not introduced in the context of like puzzle questions. But turns out that if you, this is a way of converting a uniform random variable to an arbitrary variable now. Now this is not just categorical Bernoulli, this is an arbitrary CDF. If you gave me a CDF of a desired random variable, all I have to do is I have to return f inverse u. If I can just compute this, I'm done. That's how I can sample from a desired CDF by having a sampler that just. So notice this is a deterministic function. This is a deterministic function that computes f inverse, and the only sampling that's happening is of the uniform random variable. So as soon as we see that, this then tells us how to insert neural networks in here, right? This operation of F inverse U, I can say that, hey, what I'm going to do is I'm going to replace that by a neural network. It is going to have some parameters. The input to the neural network is going to be U. U is itself a sample from either a uniform distribution from 0 to 1 or something else, and it's going to produce the output of this neural network is going to be a sample of X. I'm going to do something downstream with it, define certain losses, compute the partial of the loss with respect to all parameters, theta, including theta, compute backprop, and if it is optimal for this neural network to learn F inverse, it will learn F inverse. Maybe it's not optimal for this neural network to learn F inverse. Maybe you don't really care about generating a sample from some distribution. I don't even know what that distribution is. I don't know what the distribution of X should be, but it doesn't matter. Whatever is necessary for optimizing that loss function will get learned is sort of the argument here. So that's the idea of learning to sample, and that's the idea that shows up in generative adversarial networks. The problem being that we want to sample from complex, high-dimensional training distribution. We have no direct way of doing this. We don't have access to P of X. We just don't have it. We can sample from a simple distribution like uniform or Gaussian, and we can learn the transformation to the training distribution. So, and our sort of key object is going to be a neural network that is doing this transformation. Using similar notation to the VAEs, our input random noise now, instead of using a U, I'm going to use a Z to form an analogy with respect to VAEs and to latent variable models. This is a random variable. I know the distribution of this random variable. I typically set it either as uniform between 0 to 1 or some standard normal. And notice that this doesn't actually have to be a scalar. Z can be a vector, so there can be multiple dimensions of Z, Z1 through Zn or Z1 through Zd. There can be some D dimensions, each one of them Gaussian or uniform. Then there is a neural network that will produce an output which is X, and that's going to be I'm going to treat it as a sample from my training distribution. So that's the first idea of learning to sample, and hopefully you get the connections to inverse transform sampling, the trick of converting a uniform random variable to a desired random variable. That is a formal approach known as inverse transform sampling. Okay, so we've told you how to use neural networks to go from Z to X, where this is a sample from the desired distribution. What we have not told you is how do we compute the loss of the produced sample. And that's where idea number 2 of adversarial training comes in. The key problem, of course, is you produce a sample. I have no way of checking for correspondence against a true X, and therefore I need some other way of knowing whether the sample you have produced is actually coming from the data generating distribution. So I need to know, does this sample, can this sample come from the data generating distribution? And I need to do this without a likelihood function, because usually what I would have asked is, under the data generating distribution, what is the likelihood of observing P tilde of X? Or, generally I don't have access to P data, so I would have done under the models distribution, what is the likelihood of data that I already have? But those are not options available to me. And so the route that we're going to go, which is the route proposed in the original sort of GANS paper, Generative Adversarial Nets paper from NeurIPS 2014, is to think of this as a two-player game, as to set up a discriminator neural network that will try to distinguish between real and generated. So I much rather prefer the term generated over fake, between real and generated samples. And so the idea is going to be we're going to have a a generator network. So recall Z is either coming from uniform 0 to 1 or some standard normal. This is a generator neural network. It has parameters theta g. It is going to generate either images or sentences or something else, whatever desired output we want of X. So this is X tilde. These are samples from real images. This is our real X from P data that we have produced. This is our data set. We are going to feed one at a time these things into a discriminator neural network, which is going to have parameters theta d for discriminator, and it is going to perform a classification where real is class 1 and fake is class 0, and it's going to assign this probability, and this is going to be P real given X and X tilde. We can feed in any input, and this is going to have parameters P theta d. So that's this second neural network here. And so at that point, we are ready to set up our objective function. The objective function we're going to set up is, forget the min and the max is sitting here. Let's just look at our objective function first. Our goal is going to be, we have two types of data available to us, and so that's why we're writing the two terms separately. However, if you change notation appropriately, you'll be able to write this just as one term, but we're writing these two terms separately because it just makes it makes us easier to spot what's going on. For the real images, so for X generated from P data, so D is our probability of real given X under as a function of theta d, right? So we want the when we feed in real images or images truly sampled from the real world, we want this probability to be high, and we're just measuring log probability, right? And we want this in expectation over all of our true images. This is written as an expectation. In practice, we will approximate this by 1 over n some number of samples of log, right? So think of this just as log likelihood of your training data, but it's not really log likelihood of the training data. It's the log probability that the discriminator will assign real class, because we don't have a probabilistic model. We're not giving you P of X. We're giving you P of Y given X. Those are the difference between what's happening here. Okay, that's term 1. Now let's look at term 2. Term 2 has an expectation, first of all, over Z, which was our uniform or normal random variable. What we're doing is that Z is being fed into G, which is our which is our generator. And so this right here, this inner term right here, this is X tilde, and d theta of X tilde. So this term right here is probability of real class given X tilde. So 1 minus probability of real is probability of being called out as being correctly identified as synthetic. And so what we want is over in expectation over Z on average over the samples. And again, notice we are going to replace this expectation as some, so this is going to be some N1, this is going to be some N2 over multiple, this is a summation over Xi over your data set, this is a summation over Zi's, and so this expectation will be replaced by this, but the inner term stays exactly the same. And so what we want is, this is the probability of being the generated data correctly identified as generated, because it's 1 minus P real, therefore its probability of being identified as synthetic. Now what the discriminator wants is to maximize. This is, as far as the discriminator is concerned, this is just a log likelihood objective. You want the correct classes to be called real, and you want the fake classes to be called fake. So both these terms, as far as the discriminator is concerned, need to go up. However, as far as the generator is concerned, so the first term does not involve the generator at all. It's only the second term that the generator is involved in. And as far as the generator is concerned, let me use a different color. so it becomes clear which one I'm talking about going up and which one I'm talking about going down. So red is this and green is this, and this is the only term that involves green. And as far as the generator is concerned, it wants this term to go down because this is exactly the probability of generated data being identified as generated, and so the generator does not want that. As far we want to optimize the generator parameters so that they are not identified as synthetic. So to simplify a bit, here's the state of the world. We have discriminator output for real data. We have discriminator output for generated data. We are trying to minimize this with respect to one setting of discriminator is trying to maximize this such that d of x is close to 1 and d of gz is close to 0, and the generator wants to minimize this objective such that the discriminator is fooled into thinking the generator data is real. In a way, you can think of this as a neural network 1 producing x and a neural network number 2 serving as a loss function. So we are simultaneously learning our loss function and our sampler that produces x. These types of problems that contain a min-max, they are fairly difficult objective functions to optimize because these are called saddle point problems. Saddle point. They're called saddle point because in high dimensional spaces you have one set of dimensions where you may be locally minimum and another set of dimensions where you're locally maximum. You're looking for a point. So this is a really bad 2D rendition of a 3D figure, but you can imagine that this is the dimension where theta g is varying, and there is a third dimension where theta d is varying, and in that third dimension you have this being a local maximum point. These points are, so by design we are looking for a point that is neither cumulatively in theta d and theta g, neither a local minimum nor a local maximum, and these tend to be difficult optimization problems. These of course have connections with zero-sum two-player games and therefore Nash equilibrium. Unfortunately, while the first paper did explore that to a fairly high degree of depth, since then the literature has moved away from really diving into the details of Nash equilibrium and making, because the connection to game theory buys us only so much, because in the end this turns out to be just a difficult optimization problem, and anything that helps generate better samples is better. What you often find in practice is that in practice people will be doing alternating gradient ascent and descent. So we will sort of assume here that theta g is fixed for some number of iterations and perform gradient ascent on this objective, assuming theta g is fixed. And so the way to perform gradient ascent is you just perform, if L is this entire objective, you just perform backprop with this objective on the gradients with respect to theta d. And in the second step, you assume that theta d is fixed. And one of the terms, as soon as you assume it's fixed, does not actually depend on theta g, and so it's only the second term. So this is maybe L1, this is L2 of theta g, and you compute partial derivatives and do backprop. Turns out that one immediate optimization problem that people noticed was that if you plot this picture of log 1 minus d, even if you forget d of g, if on the x-axis you just have some probability that goes 0 to 1, and on the y-axis you plot log of 1 minus that probability, the function looks a bit like this, not bit exactly like this, and this causes a problem because ideally you'd want this objective function log of 1 minus d to be close to 0, but as soon as your that shape has fairly saturated behavior close to the optimum and really high gradients away from the optimum. And so one common trick that was proposed initially is to, instead of minimizing log of 1 minus d, you maximize log of d directly. It is a different objective. It does not actually lead to the same interpretation as a two-player Nash equilibrium. However, this objective was initially found to be better in terms of just well-behaved in an optimization sense. This part is not hard. What's hard is after you compute these partial derivatives, doing gradient ascent and gradient descent may not converge to a meaningful result. It's that part that's hard, not the computation of these objects themselves. Okay. All right. So, by the way, jointly training these two is an open research question. This, there are a number of papers still sort of trying to figure out what is the best optimization regime for this, and really the dust has not settled on this area. Okay, let's see. Yeah. So overall, here's the overview of where we are. We have a generator that produces samples, x tilde. We have a discriminator that takes in either x tilde or x and produces this label +1 for real, 0 for fake. Let's take a look at a demo. This is a really interesting sort of interactive demo for GANS produced by our own Polo Chow, who's a faculty in the he's a faculty in the CSE department. Every year we generally have some students from his lab in our class. And so if you are listening to this lecture, you can sort of say hi to Polo for me and also thank your lab for building such awesome demos. Here is an illustration. We have a data set. We can choose our own data sets. So let's say this is our data distribution. Up here, there are just two Gaussians. This is P of X, right? There's Gaussian number 1, Gaussian number 2. This is P of X. We do not know this. We can sample from it, right? This is our noise. It's shown here on the left. This is a noise which lives in 2 dimensions, Z1 and Z2. It has mean, let's say 0, and it is a unit variance Gaussian, right? It's actually maybe not unit variance, but close enough. And so that's where we are. And what we're going to do is we're going to start training this. So this generator box, which is empty right now, is a transformer. It transforms each one of these Z points to a particular point here, which will then be fed into a discriminator. So as I start training, here's what's happening. This is an illustration. Interesting. This is an illustration of the mapping from Z to X. So these are multiple samples of Z, and they are being transformed into these set of values right here. And so this is X tilde being produced as an output of this generator. And this illustration is just showing you the stretch that to a 2-dimensional space or a 2-dimensional manifold that the generator is applying to produce this sort of a sample. Both of these are being fed into a discriminator. And so the discriminator is just trying to predict real versus fake. Wherever green values are shown high, that's where that discriminator is assigning high probability of being real. Wherever purple is high, that's where the discriminator is assigning high probability of being fake. And so notice that this is a classification problem that's running in the loop of a data generation problem. What we are seeing here is classification accuracy. Let me see if I can zoom this up a bit. So notice that right here, to that same data distribution. Sometimes we get some points correct, so labeled green, we get them labeled as real. Sometimes even some real points are classified as fake, and we are performing that two-class classification on the fake points as well. There is some discriminator loss and generator loss, which is illustrated here. Let's see. And what's happening is that this GAN is really struggling to get the two modes of this distribution. It is getting half of the first mode and some part of the second mode, but it's also connecting them. It's having difficulty sort of disconnecting them into two different halves. And right here we are seeing green as the real samples and purple as the generated samples, and they are being overlaid on this figure. So you can see that over time we are at least capturing most of the mass of the green samples, even though we are unable to capture the full diversity or spread of the green samples. And that's a fairly common problem with GANs, that GANs will produce samples that tend to over time have good correctness, meaning that they will come from regions in space where true data lives, but they will have low diversity or low coverage, meaning that they will typically not have the full range of the distribution of the true underlying distribution. Sometimes this is also known as the mode collapse problem. Sometimes if the data distribution is multimodal, GANs will produce samples where they will just ignore some modes of the distribution. And so you see over time, things are getting better here. One thing that's particularly problematic here is that there are two different losses we are tracking now, discriminator loss and generator loss. So there's not just one number that we're tracking two numbers, and it's unclear whether what the optimum is. So when you solve a classification problem, it's very clear that the lower your classification loss, the better. In GANs, it's a min-max problem, and so you don't know where that min-max value is. So you don't have a good sense for are you doing well or are you doing particularly poorly. Okay. And so this is the demo, and over time you see this is getting better and better, and you can play around with different distributions of the data and see how this does. Okay. All right. And I just want to mention that, GANs have gotten really good. So these are results from 2014 at, generation of images in MNIST, and I forget what data set this is. Perhaps this is the CMU Pi data set. But initially, when GANs first came out, it was limited to these toy data sets like MNIST and Pi. But over time, people have really expanded that idea to generate high resolution images. So this was one of the first few papers in ICLR 2016 for generation of high resolution images through architectures that contain deconvolution layers. So the idea is that we still have that Z. It's a 100-dimensional, 100-dimensional Z vector. We're just going to stack it spatially by replicating it at 4 by 4 grid. So this is the same random variable replicated at 4 by 4, total 16 locations, so that it now has a spatial tensor, spatial dimension of 4 by 4, and it has, we've sort of also expanded it through a 1 by 1 conv layer to 1024 dimension. And then after that, we can have transpose convolution layers to increase our spatial resolution, ultimately arriving at a desired spatial resolution of 64 by 64 by 3, where these are then treated as RGB values that are then fed into a discriminator network. And over time, these samples have become much nicer. What you notice is that, here is, for example, a sample of an indoor space where it's clear that there is an object that looks like a bed. There are some objects that may be considered as objects hanging on the wall. Of course, we don't know exactly what that is. All we know is these are the pixel values that are generated. So if we are generating images that are near the true distribution, but our discriminators are able to tell them apart, then yes, if visually they look like realistic to you, but you have very low discriminator loss, your discriminators are doing very well, then yes, it does mean that your discriminator may be overfitting. And the way to fix that is, how do we fix overfitting in any particular case? Limit model capacity. Your model has high amounts of capacity, so reduce model capacity by taking away layers from the discriminator, making it simpler, and hopefully then it won't be able to overfit. Your second question is much harder. We don't have a good characterization in high dimensional spaces under some perceptually meaningful metric what distances in that space correspond to. But the first question is, we have a much more handle on that question. This is a really nice example of interpolation in Z space between random points in latent space. So you take Z1 as a vector, you take Z2 as a vector, you have generation 1, generation 2, and you smoothly interpolate between them. And what's interesting is that you get, reasonable looking outputs as intermediate values. And the results over the years have really, really improved in GANS. This figure is taken from this particular report, which was published in 2018. Therefore, the figure stops at 2017. But already it's pretty clear that generation of images which represent people's faces have started becoming much more realistic. There's an entire website called thispersondoesnotexist.com or .net or something like that, which every time you go to that web page, it just generates a random output of a GAN that's producing faces. New York Times 2 days ago or 3 days ago ran a story on the potential harmful effects of GANs, but it's also a testament to how believable these results have gotten. This is a paper that came out in 2018 as well. I think this was published in 2019, but this really made strong waves when this initially came out because the quality of generations in this paper are such high quality. Like, I want you to just notice that pixels are being generated here, right, as an output of a deconvolution layer. There is a clearly recognizable object. This is maybe the fourth leg isn't visible, or there are some artifacts like that, but there's an entire leg going down. There are some paws. There are 2 ears of the animal. There's like 2 eyes, a nose, a mouth. These are sort of clearly discernible features where all of this had to be learned from data, right? None of this is annotated. No parts are annotated. No objects are annotated. No classes are annotated. And all of this is generated. Notice in this image, there's a zoom in of a mushroom. There seems to be highlights or specular artifacts on what seem to be or what can be thought of as dewdrops. There's sort of texture in the grass that is recognizable. There's what appears to be a rocket about to go off with smoke behind it. There's reflection on the water. So there's a kind of detail that was really a few years ago not imaginable. There are, of course, results that still contain mixture of categories. So this is half of a tennis ball and maybe half of some animal. There are some interesting artifacts that often get created in these models. There's a nice video that someone had made of latent space cycles. This is Philip Iola at MIT, of the latent spaces in these in the Z space seem to have learned sort of meaningful dimensions of variation, when initially those are arbitrary dimensions, but later on they tend to correspond to pose of the camera or the object with respect to the camera. Oops. All right, we are stuck and can't go forward. All right. So overall, there has been really an explosion of zoos of GANs, and there's a well-maintained website of the GAN Zoo. At some point in 2018, I think it had happened that there was a hash collision of every single letter GAN. So A GAN, B GAN, C GAN, they were all taken. And so this is a really active area of research. This is kind of why I typically delegate this to the end of the semester, because really the dust is not settled in this area. I can try to teach you things about this, but chances are I'll just be proven wrong about most of the claims that we're making. If you're interested in the image generation literature, I encourage you to follow this page, which is Papers with Code. They track recent papers coming out in this literature. So overall, that's basically it for GANs. They're lead to beautiful state-of-art samples. If there are massive computer graphics applications that have been unlocked and enabled because of these models. They are really tricky and unstable to train. If you thought training CNNs was hard or training LSTMs was problematic, GANs are a nightmare typically to end up getting to work. And of course, you cannot answer any inference queries. You cannot talk about likelihoods, you cannot talk about inference posteriors, you cannot talk about conditionals, you cannot talk about marginals, none of that, which means that comparison of GAN literature tends to be heavily qualitative. You end up looking at images and either running human studies or just reporting qualitative results, which makes it very difficult to systematically benchmark and measure progress. Okay. So that's what we wanted to cover on GANs. At this point, we have done introducing everything that we wanted to sort of teach in this class. I want to take maybe 5 minutes to just sort of look back and see what we've learned in the semester. I personally find that sort of looking back at the end of the semester at the material that we covered, sometimes the terms that were somehow ambiguous or not very meaningful at the beginning of the semester tend to take on much more, they're much well grounded, and so those same expressions, you can revisit them and you're like, oh, now I understand what that means, and I get that now because I've looked at a few different instantiations of that idea. So we had told you that deep machine learning or deep learning is really 3 different ideas, and hopefully you've noticed those ideas along the different topics that we've taught you. The idea of hierarchical compositionality, the idea of end-to-end learning, and the idea of distributed representations. Hierarchical compositionality, we told you, was about composing sophisticated functions as a composite of simpler functions, as a collection of simpler functions. And hopefully that is fairly clear. In this entire semester, we've been constructing architectures or function approximators that are composed of simpler functional approximators. And the only constraint is that, as long as you have a differentiable module, you can stack them however you want. You've learned about convolutional modules, recurrent modules, various activation layers, and the only thing that you had to care about is partial differentiability. In terms of end-to-end learning, hopefully now this idea is much clearer that there is no separation between a feature extractor and a classifier, and that every activation at every intermediate module layer is both a feature and that module is doing some transformation and classification. And hopefully this idea is also clear that all you have to do is that modules are parameterized by some parameters. They take some input, they produce some output, whether these modules are CNNs, whether they're LSTMs, whether they're RNNs, whether there's anything else. All you need to be able to do is define partial derivatives or Jacobians of the output with respect to the input and the output with respect to parameters. This is used for gradient descent. This is used for continuing backprop. And finally, the idea of distributed representations, which I think is the most abstract idea and doesn't easily lend itself to an easy explanation. But we had given you this idea that, one-hot representations of these objects, and hopefully this became clearer, that instead of one-hot representations, you should have distributed representations where a concept is represented by multiple sub-concepts, if you will, and hopefully this became clearer in the context of word embeddings and tokens being represented as activations, so that then we can do sort of algebra on these topics. And we, as recently as today, we saw that when you have latent variables that are either in the case of VAEs coming from P of Z given X, or in the case of GANs coming from some standard distribution, we can treat those latent variables as distributed codes and then perform this sort of algebra in that latent variable space. And finally, we told you that this was going to be an introduction to deep learning. Hopefully that part you feel comfortable with. We told you that after finishing this class, you should be ready to get started on your first deep learning research project, which, hopefully you're using the opportunity of the class project to do that now. We were going to teach you modules of CNNs, RNNs, reinforcement learning, and generative models. Hopefully that you feel comfortable with. We learned a lot in this class, or you learned a lot in this class, which is you learned the basics of backprop, computational graphs, optimization, automatic differentiation. You learned about CNNs, the idea of adversarial examples, visualizations. You learned about RNNs and transformers for various applications. You learned about deep reinforcement learning with an entire module on policy gradients, on DQNs, and finally on unsupervised learning in the context of variational inference, variational autoencoders, and GANs. And hopefully with all this, you are ready for what is known as the archive fire hose, where papers come out and PhD students can sometimes feel that there is a lot of information being thrown at them. Hopefully what we've taught you is that most deep learning papers are coming from some low dimensional distribution, and if you just get a handle on Z, those underlying latent ideas, you actually have a much better chance of understanding and categorizing and finding the diffs in these papers. One thing I really want to stress on is that this class is not static. Every year we make changes to this class, including this year. Your transformer lecture was new this year. Every homework contained a new theory question that your TAs made. Every homework contained a paper reading assignment that was new this year, and the papers were chosen by the TAs. We are constantly experimenting, which means we need feedback. And if you think about this, I am performing RL at the level of semesters, right? There's a long delayed evaluative feedback. I take a long chain of actions. I work with a team of TAs, we put together a semester, and at the end of the semester, we get sort of stochastic sampling of feedback on how we did at various points of time. And there's a very long feedback, and the only way for me to drive down the variance in the estimate of the gradient of the change in my policy is to ask for as many data points as I can. So your feedback is highly, highly appreciated. If there's something that you liked, tell us. If there's something that you didn't like, tell us. We can change it. For example, I've I do this recap of the previous lecture in the beginning of every lecture. I've received feedback over the years that it's useful, but there's a small minority feedback that I often get that it can take a lot of time, that it seems repetitive. I'd love to revisit that question. If you think that it's too long, just let me know. But so overall, I'm going to be annoying over the next 2 weeks or so. You're going to be hearing and receiving reminders from me about this feedback. Please do complete it. We highly value and appreciate it. Okay, and that's basically it. We hope your future learnings are deep. Thank you for joining us this semester. Hopefully, I'm confident you'll find value in things that we're teaching you. Stay in touch and let us know how things are going with you. And I am happy to now take questions.